Okay, so welcome back. So right now we try to introduce the more exercise, and we will better understand what are the physical meanings for the energy equations and what is applications to the real case. So this is the tank, and the tank connects to a very longer pipe. Do you see the pipe? For this pipe is very longer, is 2,000 meters. Okay, and we have the diameters for this pipe is the 20 centimeters. So we have the diameter for this pipe is 20 centimeter equal to 0.2 meters. And when the question directly tell us the head rolls for this uh, pipe is 0.020 divided the diameters, and we know that the velocity square divided 2g. And I just put the right hand side for the general flow. For the head rolls for the pipe problem is the frictional F here. So usually the different condition of the pipe, we will have the different friction coefficients. And in our exercise here, we use 0.02. And you know that the L increase and the head rolls also increase. And when the diameter decrease, so the head rolls increase also. And the velocity speed out, and then the head rolls also increase. So it just make sense for the physical meanings for the head rolls equation shown here. And what the condition we have, we know that actually the discharge for these problems is 0.06. Okay, so what is the problem? The problem is what's the pressures in the pipe. So we would like to know the pressure in the pipe. And so we go back to see how to solve these problems. So we just write down the energy equation here, and we actually know that the pressures in the inner net here, the pressure, because the point is posed at the atmospheres, so the gauge pressure is equal to 0. So we don't have these items. And we actually know the elevations at the point 1 is the 100 meters. So here we have the 100 meter. And usually for this kind of the problem, we know that the V1 at the water surface is always quite smaller than the V2. The V2 is the velocity in the pipe. Okay, so we just these V1 items, and there in our system there is no pump, and there is also no turbine. So we just make the equation balance. But we have the E2 is our unknown parameters and divided the gamma, and we have the V1 here, and we move the V2 to be the minus, and we move to the alpha 2 V2 squared divided to G, and we just minus the head rolls for our problems. And the P2 actually equal to the gamma and D1 minus D2 minus alpha 2 is equal to 1. So we don't need to alpha 2. So here I only write down the V2 squared divided to G. And minus the H head rolls. Okay, so what we already know, we know that Z1 is 100 and the Z2 is 20 meters. And we don't know the V2, and we can compute the heteros by these equations. So how can we compute the V2? Since we have the discharge, and the discharge divided the cross-section area, and then we will have the V2. So this is 0.06, and the area is the 4 over pi d squared. D squared is 0.2 squared. So you can use your calculator to compute the velocity. Here 0.06 divided pi divided 0.2 divided 0.2 and multiply the 4. So the velocity for the V2 is 1.91 meter per second. And what is the heteros? The heteros in here is 0.02 and multiply the length. The length is 2000 meters and the diameter is 0.2 and the V velocity square in here we have 1.91 square and divided the 2g. So we can compute the heteros. So the 1.91 square multiply the 2000 meters divided the 0.2 multiply 0.02. This is the frictional coefficients. Divided the 2 and divided the g is 9.81. So the heteros for this problem is 37.22 meters. So we just put the number, go back to here. So the gamma is for the water is 9810 multiplied 100 minus minus 20 meters minus the 1.91 square divided 2g and then minus 37.22 meters. Okay, so the 80 minus the 37.22 and the minus 1.91 multiply 9.91 velocity divided the 2 and divided the 1.81 gravity. So and then multiply the 98110. So we compute the final answer is equal to 417.8 kilopar. So if you compare these pressures inside the pipe to the atmosphere, pressure is 101.3 kPa. It's around 4 times compared to the environment pressures. So this is a very large pressure in the pipe. Then we consider the problems. Could we just use the Bernoulli equation to solve this problem, deal with this problem? The answer is not. We cannot use the Bernoulli equation to describe the problem, deal with the problem, just because the problem, the Bernoulli is assumes invisible, but in our problem, we satisfy the L P ratios is quite far away from the 5. So in that case, the viscous effects are significant. So we cannot only use the Bernoulli equation to deal the problems. So that is why we need the energy equations. And the importance in our questions directly tell you the heteros following these equations. And we just put the general form for head rows, but the key knowledge for the head rows is the friction coefficient here, F. So as the figure I push here, I put here is this is the frictional coefficient as function of the Reynolds numbers. As a Reynolds number, we know that the higher Reynolds numbers indicate the flow condition is turbulent. At the lower Reynolds numbers, we know that is the laminar flow. So since the flow conditions from the laminar to the turbulent flow, the friction will decrease. So this is the ideas and the basic concept that I would like to let you know. So and then we just move the energy equation to the power equations. As I mentioned before, we know that the power equal to the m rate gh. If we would like to interesting for the work rate for the pump and the work rate for the turbine, and then we just simply apply a different head. And in general form is P power equal to n rate gh or the gamma qh, which are based on your questions, based on your problems, and you select the formula you need, and you compute directly the powers. So the table just summarizes all of the power equations. As we know, P is equal to F force multiplied velocity, or if your problem includes the rotational motions, so your power is equal to the moment multiplied by the angular speed, or just directly you have the head, so you can directly compute the power by the m rate gh or the gamma qh. Only one difference is if you have a discharge number directly, and you can compute the power by the gamma qh. Okay, so right now this is the problem included the pump. So this is the inner pipe, and this is the pipe flow. So in that case, because it is inner pipe, so we have additional pressures inside, right? And we assume the pipe with the constant discharge is 0.5 meter cubic per second, and the diameter of the pipe is 0.5 meters. So we actually know that the elevations for section 1 is 30, for the cross section 2 is 40. So the bump just rising the water high 10 meters. And we have the pressure at the section 1, 70 kilopascals gauge, and the section 2 is 350 kilopascals. Okay, so what is the power in kilowatts or and in HP mostly supplied to the flow by the pump? So the idea is we need to compute HP first, and then following the power equation, we know the power is equal to m rate gh. Okay, and if we have the discharge, so we know the power is equal to the gamma qh, right? So the key question is HP. So if you go back to see the energy equation showing here, so actually we have the pressure already, right? We have a pressure 1, and we have a pressure 2, and we have the elevation 1, and we have the elevation 2. And for these problems, we didn't know the velocities, but because this is a constant discharge and we assume the diameter didn't change of the pipe, so based on the continuity equation, we always know that the V1 should be equal to the V2 because the cross-section area didn't change it. So we don't have the V1 and the V2 items, and we have the pipe. So we don't have the turbine, and for this question, the directly tell you the header loss equal to the 3 meters here. So the unknown parameter is the HP. So we just put the number inside the equation. So the P1 is the 70 kilopar divided the gamma because the problem is the water. So 9810 plus Z1 is 30 meters, and we don't know the HP. And the right hand side we have the 350 kilopar divided 9810 and plus the 40 meters, and we have the header loss 3 meters. So we just make the equation balance. So we just compute the number here first. So it's 350 multiplied 1000 divided 9810. So it's equal to 35.67 plus there is a 40 and plus 3, so it's 43. And then we compute this number is minus the 70 multiplied 1000 divided 9810. So it's equal to 7.14, and there's a minus 30. So we can compute the final HP is the 35.767 plus the 43 minus the 7.14 and minus 30. So the head for the pump is equal to the 41.5 meters. And we go back to see the power equation here. So we have the gamma is 9810 and the discharge is 0.5 and the pump head is the 41.5 meters. So we know the powers for these problems is around the 203.7 kilowatts. And the question also requires you answer the unit in HP. We know that the 1 HP is equal to the 746 watt. So we just divided this number by the 746 watt. It's equal to the 273.1 HP. Okay, so we similar to the answer shown here. So it's a very normal questions. We just based on the energy equations and get to tell you how the work by the pump. So it's the question shown here. Usually the pump have to operate it when you support the electric power, right? So since we know that the power supplied by the pump around these numbers, we need to provide additional electric power to supply the pump operations. And usually we know that the electric motors will include the energy loss because the pump itself is not always 100% efficient. What's the problems? The problem we need to understand the efficiency of our equipment, such as the pump and the turbines. So the idea is we have the electric power supply and to and supply the electric motors and the pump start to operations and finally moving the fluid flow. So we know finally the combinations for the efficiency is around the 45 percentage. This is the pump supply to the fluid and the efficiency number here. And in other words, if we consider the wind power plant, so the air moving the wind turbines, and then we have the energies powers, and we have electric generators, and finally we have can provide the electric powers. But there are still some discount. So the combined efficiency finally is 32.4 percentage. It's not really high enough. So in real case, we know that the most of the energy dissipates into the environment by the heat. So it is the efficiency is very important for our problems. Okay, so actually we have the shaft provide the power, but we know that there are some discount, so we need to multiply the efficiency. This is the true power supplied by the pump, and this is the true power supplied by the shaft. We still need some efficiency coefficient here. Okay, so let's consider this take into account for this efficiency. So this is the hydraulic power plant, and we have the elevation 61 meters, and there are some power turbines, and to create the power generators. So we know that the discharge for this problem is the 14.1 meter cubic per second, and we know that the elevation start from the 51 meters and drop to elevation 0 here. And we know that the head loss for these problems, total head loss is the 1.5 meters. Okay, and the combined efficiency of the turbine and the electrical generators is the 87 percentage. So what is the power out for these problems? So again, first we need to know the headers for the turbines, and then we can compute the powers equal to the gamma Q head turbine. But we know that the output should be equal to the efficiency multiplied by P. This is the true powers provided by the turbines. So the key questions we know we need to go back to see the energy equations here. So our problem, this is the cross section 1 and this is the cross section 2. So they expose at the atmosphere conditions. So we know that the gauge pressure is R equals 0. So we don't have the P1, we don't have the P2. And since we also know that the velocity at the water surface also change, the change of the water surface of velocity is small, so we don't have the V1 and the V2 problems. So we just make the balance, we don't have the bump head also. And for this equation, we only have the V1 on the left hand side, and the right hand side we have the V2. plus the turbine head and plus the header rolls. So we can compute header turbine very quickly with just V1 minus the V2 and then minus the header rolls. So G1 is 61 minus 0 minus 1.5. So we know that the turbine head is 559.5 meters. So we can compute directly the efficiency, the out. The efficiency is 0.87, and we have the gamma is the water 9810 multiplied the discharge is 14.1 meter cubic per second multiplied 59.5. So after the powers, use your calculators. 0.87 multiply 9810 multiply 14.1 and multiply 59.5. So this is around 7.1 million watt. Okay, so this is a very simple questions. If we try to estimate the powers for the turbines or the pump, we need to know the head first. And based on the power equation, we can compute the power by the gamma Q head height. And then there's also our problem include the emissions, so we need to have some discount. Okay, so for this problem is quite easy to figure out. We just have the elevation header to transfer to the power generators, but the path around the pipe we have the header rolls, so that means the power is directly proportional to the elevation head changes and need to minus the header rolls. Okay, so this is a slide just we stopped here to clarify some ideas, and so we just provided the contrasting the Bernoulli equation and the energy equations. So the left hand side is the Bernoulli equation and the right hand side is the energy equation. Clearly, as we see that the difference is the HP, HT, and the header rolls. And we know that the Bernoulli equation is derived based on Newton's second laws, F equal NA. And as we start from the F equal to NA and we derive the Euler motion equation first, Euler's equations, and then we just consider the situation in the steady flow and the incompressible flow, and also we don't consider the viscous effect. And the right hand side, the energy equation is derived based on the ideas is the first law of the thermodynamics that indicate the energy conservation. And we use the Leonard's transport series, and we use the extensive properties, the energies. So we can combine two equations together. So, and we based on assumptions of the steady flow incompressible, but the significant difference compared to the Bernoulli equation is the viscous effect is very important for the energy equations. That's why we have the header rolls and we have additional power supplied by the pump and the turbines. Okay, so but the layer still have the minor header rolls due to the pipe transitions. So what are the meanings? And here we meet the problem. We graph the header rolls for the minor header rolls or transitions problem here. So as I mentioned, we can based on the momentum equation, continuity equation, and the energy equations, and we can derive what is the HL for the transitions problems. So if we see that there is one of the transition problem, why? Because we know that the inner pipe diameters will be changed to large. So let the D1 change to D2, and they will have some heteros for these transitions changes. And we assume the turbulent flow conditions, so the alpha is quite close to 1, and we start from the momentum equations. Our idea is would like to know what is the answer for the heteros for these problems. So the momentum equation tells us the external force is equal to the M2 rate plot multiply the V2 minus the N rate 1 multiply the V1. And so what is the external force? We know that it is inner the pipe, so we have the pressures in here, and we have the pressure in here. We have a P2, and there is the P1. So, but the P1 is acting on the control volumes, the control surface area is the A2 area, and there is also the A2 area. So you see that the force, the pressures for the inner cross sections, the P1A2 and the V2 minus the V2A2. And what is this? This is the total weight in the control volumes, the weight. And we know that the incline angle is alpha here, so we have the incline angles. So A2 area multiplied the length is the volumes. So the A2 multiplied this is the volumes in control volumes. And why we need to convert to the, the sine alpha, because we would like to project the force along the straight line directions. So we have the sine alpha here, and multiply the gamma. So this is the total weight contributed from the control values. Okay, and based on the continuity equation, we know that the mass flow rate 1 equal to the mass flow rate 2, and the mass flow rate 1 is also equal to the low V1A1, and the mass flow rate 2 is equal to the low V2A2. So we can just push the number, go back to the equations. There's the P1A2 minus the P2A2, and then minus the gamma A2L sine alphas, and equal to the M2 rate here. So the low V2A2 multiply the V2, and minus the M rate 1 is here. The low V1A1 multiply the A1. So in that way, we divided the A2 for these equations. So there will be the P1 minus the P2 and minus the gamma L sine alphas, and equal to the low P2 square minus the low P1 square A1 divided the A2. Okay, and we also divided this equation by the gammas. So we know that the P1 gamma minus the P2 gamma, and there is only have a rho L sine alphas, and this is divided the gamma, so there we only have the G P2 square minus the G P1 square A1 A2, right? And you take a look, the L sine alpha is actually equal to the elevations D2 minus the elevation Z1. Okay, so we can rewrite the equation here. This is the minus the D2 minus Z1 and equal to the V2 square G minus the V1 squared G A1 A2. Okay, so this is the equation derived based on the momentum equations and the continuity equations. So we just put our equation here, and if you put the number inside, based on the continuity, we also know that the V1A1 equal to the V2A2. So you just push the relationship back to the equation here, and you can reorganize the equation. You have the equation 1. This is the equation 1 derived based on the assumption of the momentum equation and the continuity equations. And the same for this problem, we apply the energy equations. So we know that the P1 divided the gamma and the 2G over V1 squared minus plus the V1. And for this problem, we don't have the pump, and we also don't have the turbine. So we don't have the two items. So this simply equal to the V2 divided the gamma and the 2G over V2 squared plus the elevation 2 and also plus the header rows. So you just make you have a combine the equation 1 and the equation 2. So you can reorganize the equations. So I may use the equation 1 minus the equation 2. So this is a minus this. Okay, and you may just compare each two equations together. You know that they're same items and the same items, and we have V1, V2, so we can cancel out these items, and then you only have, so there is the minus V1 squared to G, and here is the V2 squared G minus the V1 V2 G and minus the V2 squared 2G and minus the HL. Okay, so you just reorganize the equation. So you just put the same parameters together. So there is the 2G V1 squared, and there is minus, sorry, there's a minus the G, and there is V1 V2, right? And we can compute this combine two items for the 2 square. So there is the plus the 2G V2 square. Okay, and you take a look, we can also have a 2G here, and then there's a 2 times V1 V2, and that means we can 2G take outside, and the inside we only have the V1 squared minus 2 times V1 V2 plus the V2 squared. So this is equal to the 2G over V1 minus the V2 squared. Okay, and if we apply discharge fluid into the reservoir, and then the V2 is equal to 0. So we only have these items. So finally, we can derive the HL is equal to the 2G over V1 squared. So that we only based on the momentum equations and the continuity equation, the energy equation, and we can derive what is the header rows for the transition problems. So actually, this is the general transitions problem include the header rows. So the KL coefficients, it depends on different conditions. So let's say different conditions, we have the K numbers, have a different K numbers. So you can, based on your questions, and select which condition you used, and from the table you directly know the K coefficient for your problems. Okay, So this is very important. And another questions per problems we would like to discuss the force on the transitions. So again, because the problem also the transition problem, so we need to apply the energy momentums and the continuity equations. So that's our problems. What's the problem? The problem is the what the horizontal force is required to hold the transition in the place. So this is the transition that start from the B1 to B2. Okay, so our large force need to require to hold pipe don't move. And we know that the rate of the Q is the 0.707 cubic meter per second. And the diameters for this the D1, D2 shown here. And we have the heteros, and the heteros is based on these equations by the transition problems, and the coefficient k used in here is 0.1. So the first we just based on the momentum equation, we know that the f(x) is our answers, but we didn't know, and we just plus the p1a1 and the minus the p2a2 is equal to the m rad v2 out minus the m rad v1. So we have the discharge, and then we can solve the v1 by the q divided the a1, and the v2 derived by the q divided the a2. So we have a1, a2, and what is the mass flow because we have the q. So below q we can compute the mass flow. And the question tells us the pressure one, but we didn't know the pressure two here. And the FAK is also the unknown parameters. So we need to have the additional equation to uh, deal with the P2 problem first, and then we go back to these equations, and then finally we can find out the FAKs. So because of the time limitation, so I don't put a number inside the equation one, and you can take home math homework and you can finish this exercise. Then the answer is shown here. So what is the second equations? The second equation we can base on the energy equations. So we this is an inner pipe, so we have the pressure one, we have the pressure two, and we have the V1, V2, but they are located at the same elevation. So we don't have the difference in the elevations. And the system don't include the pipe and the turbines. And we have the heteros based on these equations. So based on the energy equation, we can have the P2 numbers. And we can put the P2 number back to the equation 1 and try to understand to figure out what numbers of the BAKs. So this is your homework. You can calculate the answer by yourself. So this is the end of these chapters. As I mentioned in the first slide, this is very important if we have the HGL and the EGL, and we can describe the energies, describe the pressures and the velocity variations in our fluid field. So what is the EGL? The EGL is the energy grade line. We call that the hydraulic, also call that is the 能量迫降线. And the second is the hydraulic grade line. We call that is the 水力迫降线. Yeah, so see that the certain definitions of what is the difference compared between the EGL and the HGL. You see that the EGL is the velocity head, velocity pressure head, and the elevation head. This is similar to, we call that the total head. But the HGL only have the pressure head and elevation head. So usually we call that is the piezometric head. And this is very important to find the inside and helps one locate and correct the trouble spots in the systems. Usually we are interested in the low pressures. The lower pressures will have the cavitation problems. Okay, so how to use that? As you see, this is similar to our first exercise, and we have a tank, and the tank connected with the pipe, and there is a solid line is the EGL, and the rotation line is the HGL. So you see there are significant the gap between the solid and the rotation lines. As I mentioned, the EGL is a total head, and the HL only have the pressure head plus the elevation head. So the gap between the solid line and the dash line there is in relatively to the velocity is greater divided the two G's. And you see the gradient of the solid line and the dash line are the constant. So why the line will decrease when the when the length of the pipe increase? So that means this is the gradient is equal to the ratio between the head rows divided the L. This is we call that is a hydraulic gradient. So the slope of this solid line and the dashed line is equal to the hydraulic gradients. Because we know that if the L increase and the head rows also increase, right? So increase in here, and then that means the physical meaning is when the length of the pipe increase and the head rows will increase also. So, and then you take a look for the first point here, the starting line and the dash line with has the same starting point. Because in here the velocity is near zeros, so there is no any difference between the EGL and the HGL. So the starting point is at the same, and then we'll split, and then we'll separate after here, and the gap is equal to the V velocity squared divided by 2G. So actually the EGL and the HGL, you can understand the conditions of your systems. And if your problem include the pump, and then you will have the HP. So at this after this point, the header will increase by the HP numbers. And if your problem have a turbine, so you will drop rapidly after go through the turbines, because this is the energy is out of the systems. And if you have some transition difference, okay, so this is the big diameters, and this is small diameters. And we know that the D1 larger than D2. Again, so and the velocity in here, because the diameter is larger, so the V1 is this V2. Since the D1 larger than D2, so the V1 should be smaller than V2, right? And we tell you the solid line and the dash line, the gap between the solid line and the dash line is related to the V2 velocity squared divided 2G. So in here the V1 is small, so the gap is smaller than the right hand side. This is a larger gap. And you see the gradients, the HL divided L also difference. The hydraulic gradient in the right hand side is larger than left. That's because the V2 velocity is increased and the diameter is become smaller. And based on the header rules, you know that the L divided D ratio square is proportional to these numbers. So the small d and the higher velocity will increase the HL faster. Okay, and then this is the problems you see because the diameter becomes small and the cross-section area diameters smaller along the right hand side, so the velocity will increase. So you see the gap will increase when the fluid flow to the right hand side. Okay, and this is what I mentioned before. You see the HGL line and the EGL line is lower than the pipe, as indicate there are some negative pressures. And if we see this condition, that means the cavitation will be occurred in our systems. So normally the engineering just draw the HGL line and the EGL line to see where is the cavitation site for our problems. Okay, so I would like to emphasize this is very important for our chapters. If you can draw EGL and HGL line, and you can better understand what is the pressure distributions and the velocities variations in our problems. Okay, so the key to knowledge is you need to know what is the gap. The gap is contributed from the velocity difference. Because the HGL didn't account the velocity head, and what is the gradient related to the header rows and divided the pipe length. We call that is a hydraulic gradient. Okay, and this is important. If you see the grade line lower than the pipe, that means there are some cavitation phenomena. Okay, so we have the one exercise which just provided some conditions and the place for the HGL and the EGL lines. As you see in our problems, we include the pipe, so there are some header jump. The line should be jump out, go through this point. Okay, so you see we draw the EGL line is a solid line and the HGL is the dashed line, and after go through the pump, so the height will be increased, and then we will the total case with the constant gradient. And as I mentioned, this is a hydraulic gradient. Is header rows divided the length of the pipe, and what is the gap? Here is a small gap between the solid line and the dashed line is equal to the b squared divided 2g. This is very important. If I provide some conditions and the parameters, how can you draw the EGL and the HGL lines by yourself? Okay, so in next semester we have the header rows experiment for the pipe flow. Okay, so it's just a very simple concept. We have the energy equations, so we can try to better understand the header rows. So as we know, the header rows is the most important coefficient is the frictional coefficient, and the frictional coefficient is a function of the Reynolds numbers. So for this experiment, we would like to conduct different flow conditions, and we know that measure the flow velocity is And based on these equations, we can compute the frictional force, frictional F, and we just compare different flow conditions. We have for real numbers. The real number defined in the following these formulas, and then we can have this conduct a series experiments and try to understand the relationship between the real number and the frictional coefficients. So this is our laboratory experiments in the next semesters, and the topic concept related to the head rows. Okay, so we finish the chapter 7 and a little bit fast, but I will highlight the